Pragmatic verification reuse in a vertical world. Abstract. Successful application of the plug level verification reuse to improve the effectiveness of the top level environment by providing additional check, coverage, and messages, in some case stimulus, which as well as detecting more bugs helps speed up the work for other level defects by providing improved internal visibility and enhanced bug isolation. Despite these benefits, consistent efficiency reuse is simply not being achieved in many companies. This paper visited the vertical reuse problem from a fresh standpoint and addresses the fundamental issues involved, provide a comprehensive set of the programmatic reuse guidelines, and also suggests to go about retrofitting reused code to existing plug level environment. Introduction. Successful application of the plug level verification reuse improve the effectiveness of the top level environment by providing additional check, coverage, and message. And in some cases, stimulus, and which, as well as detecting more bugs, helps speed up debug for other system level defect by providing improving internal visibility and enhanced bug isolation. The detailed understanding of the plug level protocol and associated expertise has been built into automatic checks such as a scoreboard and the ability to collect functional value coverage based on a coherent transaction and a capability to provide concise and informative messages based on signal decoding is of course also reused. This allowed the top-level team to concrete more on appropriate concern, such as the overall functional correctness of the application, external interface behavior, and correct and module and self-system interaction, access to the shared resources, and low power operation, performance and interconnected verification requirements. The use of a plug level verification environment at the top level is potentially well supported by the modern verification methodologies such as universal verification methodology. However, the evidence from the course of the project in many different companies is that a successful effectiveness of vertical use is simply not being consistently achieved. This paper reached the vertical use platform from the fresh standpoint and addresses the fundamental issues involved. Provides a comprehensive set of the pragmatic reuse guidelines and also suggested how to go about retrofitting reuse to existing plug level environments. The discussion is essentially language independent, but any major differences between the E and the system value methodology are highlighted well. The appropriate, however, UVM terminology is used throughout. Chapter 2. Vertical and horizontal reuse. The word of the verification is not flat. The terms vertical and horizontal are used to describe the context into which verification artifacts are reused. In this respect, horizontal typical means the using a verification component in a different system or a project, but all roughly at the same level of abstraction and with the same functional role. The vertical use, on the other hand, refer to using a verification component in a different hierarchy level and usually with an implied change of the role. The full example, the verification component used in the plug level, subsystem level, and top level environment within the same project exhibit vertical use. In this case, we would expect the stimulus to be nested inside a higher level stimulus until the stage while the associative interfaces are no longer external signals, but embedded connections internal to the design, at which point the role of stimulus generation would no longer be applicable. This paper focuses on vertical use attribute and especially those related to the change of the role when going from the plug level to top level verification hierarchies. So comprehensive plug level verification is essential to full achieve success. But at the end of the day, Nobody takes out a block. It is the top-level chip that brings in the money. In that aspect, we live in the vertical world. Chapter 3. Top level or bottom up. The two engineering paradigms of the top level and bottom up design can also be applied to the concept of the vertical use. In an ideal world without a real project pressure, it would be reasonable to assume all verification environments were composed in a bottom-up manner, where block level component environments are combined and layered in the well-structured manner until we arrive at the top of the level environment with implicit reuse. Indeed, standard verification methodology often portray this as normal practice rather than an ideal goal. The evidence from any of a project at a variety of the client is that the real world does not conform to this ideal. The main reasons for this are threefold. Firstly, the top-level verification environment has different requirements. They must support a highly constrained real-life scenarios and directed tests, perhaps also running real software from, and in many cases with accurate behavior models for analog block integrated into digital chip. Secondly, these top-level environments are almost always in the critical paths are therefore developed in parallel with the corresponding block-level environment. Thirdly, the sheer variety of the quality and capability in what is often a collection of block-level subsystems means that the forming a coherent homogeneous amalgamation that fits all the top-level requirement is just not feasible. So this leads to the situation where the top-level environment may be developed in a top-level manner in order to achieve each goal independently from the block-level test bench development. As a later stage of the project, block-level verification components are imported to enhance the effectiveness of the top-level environment by supplementing the external device under test, operating validation with comprehensive internal checks, coverage, and messages. Chapter 4 is verification requirements. The top-level test benches has quite a specific verification requirement that differed from the comprehensive but isolated constraint random constant dealt with by the top level of the block level environment. Top level requires include functional correctness of overall application, integration of all modules and subsystems, access to shared resources such as memory and bus structures, and operation with a realistic clock and power domain behavior, overall performance of the system, parallel external interface behavior, connectivity of the all blocks and the subsystem. We cannot achieve a closure of all of these verification requirements by looking only at the external pins in a complex top-level chip. These requirements mean that we need measurement coverage and check operation of the critical functional data paths inside the duty, including validating relationship between blocks while running top-level test scenarios. If the top-level test fails to address these concerns, they represent significant risk to overall quality to the application. One additional advantage of the reusing the block-level verification environment in the top level is that we close the loop in the functional expectation for the block. Often, a block that is a comprehensively validated standalone system finds itself under different and unexpected conditions in the top-level environment, for example, starved of the resources. So sometimes the block-level environment requirements are themselves improved by the application of reuse. Chapter 4 is debug requirements. It's not enough to provide a top-level verification environment that proves the functional operation of a perfect chip. The path to the perfection will not doubt include failures that need to be debugged effectively and efficiently during the top-level simulation. Time taken to debug failure, especially in the top-level environment, is probably the biggest drain on engineering resources at a later stage of the project can put the simulation effort firmly on the critical path. Additional internal checks and Message can a long way to helping debug requirement become a reality. Localized checking at the block and subsystem boundaries improve the observability of the failure and can quickly isolate problems. Additionally, informative messages for operational paths and internal interfaces are invaluable for identifying which aspects of the chip are behaved as expected even though the overall test indicator fail. So the best way to achieve this level of the bug isolation within the complex top-level environment is by making the extensive use of block-level artifact operating in passive mode as detailed in the next section. Chapter 6 is active and passive operation. All modern verification methodologies make a clear distinction between the active and passive operation of verification components and environments. They can be summed up as follows. Active components provide an effective stimulus driven to the duty, and passive components do not provide or affect the stimulus in any way. In this context, stimulus is more than just generating input to the duty from a proactive method, but also includes providing responses from the reactive slaves, clock generation, and side effects like delays. All of these are affected by the active component and non-affected by in any way by component operating in passive mode. Both functional capability in the runtime architecture of the corresponding verification environment affected by the active or passive mode setting. Consider, for example, the active block level verification environment shown in Figure 1. So, the Figure 1 is the active block level environment. So in the active environment shown in Figure 1, stimulus of the provided by sequencer and drivers, and a proactive method generates request stimulus, and preactive slave generated response stimulus. Checks are performed by the interfaces monitor and scoreboard, and coverage is collected by the monitor. Messages are generated by all components. The corresponding passive version of the block level verification environment is shown in Figure 2. Figure 2 is the passive block level environment. In the passive block level environment shown in Figure 2, the no stimulus is performed by the passive component in the environment. Sequencers and drivers are not present. Checks are still performed by the interface, monitors, and scoreboard. Coverage is still collected by the monitor. Messages are generated by the remaining component. Typically, the passive mode is used in situations where the relevant duty block is instantiated in the higher level subsystem or top-level chip. In this case, the verification stimulus is provided by active component of the verification environment outside the scope of the reused block level verification environment. This is illustrated in Figure 3, which shows the passive block level verification environment being used in the context of the top-level test bench. Figure 3 is a passive block level in top-level environment. In this case, all of checks, coverage, and available debug methods are used to ensure the more effective validation of block in the context of the top-level duty, as well as supporting more comprehensive top-level test bench operation. Active and passive mode. In order to select between the active and passive mode of operation, all relevant sub-component must include an active and passive configuration flag. Note that the complete block level environment must take into account active and passive settings, and not just the lower level interface verification components. Often engineers make reasonable jobs of the low-level verification component, but fail to implement correctly structures active and passive mode setting for the and closing environment. The intent is to provide a top-level integrator with a complete and properly encapsulated passive environment that contains all of the necessary low-level verification component configured in appropriate manner. Complete environment must consider active and passive configuration, not just the verification component. The active and passive mode setting should be used during the creation, build or generate phases of the environment and affect the actual construct instances of the component within the agent and the environment classes. The active components like sequencers and drivers are not constructed in passive mode. Do not create the active component during the passive mode construction. Since the active components are not present in the passive agent or environment, it follows that we can connect their transaction level modeling, TLM ports, or assign the internal pointer references to other components. Do not attempt to connect to active component during passive mode. B. Scoreboards. Scoreboards are a special kind of checker that perform the comparison between transactions published by the different monitors in the system. These checks may comprise transformation checks, where the transaction type is comprised transformation checks, where the transaction type is modified to generate a different transaction type, or they be validated propagation and distribution for transactions of the same kind. Scoreboards are crucial to validating their functional patterns through the design, and therefore the use of these block-level scoreboards has extremely important checker capability to the top-level environment. Since these scoreboards live in the passive environment, the transactions testing the full scoreboard comparison must come from the passive component and not active component, which are present in the passive architecture. However, even though this is a fundamental rule in each of the standard verification methodologies, it also appears to be the biggest single violation in the block-level architectures, and it is also hardest architecture defect to recover from when attempting to retrofit verification reuse capability, as discussed later. Do not connect the scoreboard to active component. The main cause of the bad scoreboard connectivity appear to be that some verification engineers recognize a shortcut is possible, which saves the effort of for monitor development, but overlooked the fact that the vertical use is totally comprised. So specifically for an active environment, the transaction field of information typically exists in the form of the sequenced item that is provided to the driver. It's easier to send this sequencer item, which represents a request to driver transactions, to a scoreboard than the correctly implemented monitor to the fully decode interface signal. The observed traffic construct the transaction object from this and then posted the scoreboard. However, the robust functional verification, the monitor must independently decode the actual traffic reserved signals for the interface to publish this information via the analysis ports. This ensures the reliable checker operation and support passive reuse. C. Functional checks. In addition to the transaction comparison down in the scoreboard, all functional checks for the transaction content and protocol behavior should also be done in passive component, typically monitors. Everyone knows that. Now then, do people choose to implement timeout checks and error messages inside the drivers? In principle, drivers may need to check some aspect of the protocol behavior in order to correctly react to the duty responses and recover correctly from unexpected failures. But the actual protocol checks and error messages need to be implemented independently inside the corresponding monitor as well. Perform functional checks in a passive component. The protocol operation and timing checks are often implemented using system value assertion SVA, which option notionally belong to the monitor but must be implemented outside the class-based environment, usually in the corresponding interface construct. Since the interface is also instantiated passive environment, these SVA protocol checks are all still operational in passive mode. D. Functional coverage. The vast majority of the functional coverage should be implemented in a passive component to allow for reuse at the top level. This approach also tends to strengthen the quality of the functional coverage, since, for example, we do not cover that we requested a particular transaction to be sent to the duty, but later we covered what was actually sent when the monitor has decoded the observed traffic. Occasionally, some stimulus coverage is deemed appropriate and cannot be measured by the monitor. For example, some error injection mode that would result in a traffic that cannot be reliably decoded by a monitor. So in such cases, a separate isolated covering driver is appropriate, but cannot of course be used in the top-level environment and therefore does not contribute to verification code for top-level. Collect functional coverage in a passive component. E. Configuration updates. As often the case, there is a pseudo-static configuration field related to protocol operation that must be kept up to date to ensure the correct functional operation of the verification environment. These settings can change during the running of a test, typically in response to some traffic in one or more interfaces to the duty. Since the value of this configuration field is affected by the stimulus in the block level environment, it is tempting to update the configuration directly from the sequencer driver. However, since these active components are not present in the top-level reuse scenarios, and it is still crucial to maintain the configuration accuracy, then these fields need to be updated by passive component, typically monitors. Update configuration only from passive component. F. Information messages. Something that is often overlooked in is the importance of the preserving the relevant informative messages in passive reuse scenarios in order to help debugging failures and isolate the working aspect of the top-level chip. All subcomponents and methods in the verification environment are allowed to generate informative messages. However, only the messages from the passive component will be available when the environment is used in passive mode. Generating importance messages in passive component. G. Warning messages. Many block-level verification environments include the capability to inject errors from the active component as part of the stress test features for a comprehensive block-level verification requirement. Typically, the transaction sent to the duty with the illegal contents are not reported as an error under the circumstances, since it would be the cause of the test failure, but rather the warning. The verification environment will respect the specific error detection and recovery operation from the duty, as well as a result of the error injection. If it does not occur, then a real failure message is generated. In top-level environment, we may want to reclassify the illegal transaction arriving at an embedded block as an error, since this could help isolate the real problems in the situation where the upstream RTL block generated illegal input signals. Under these circumstances, the monitor, which is always a passive subcomponent, even though it is present in both active and passive environment, would use the active and passive flag setting only to determine the message severity. Consider promoting the warning messages to the errors in passive mode. H. End of the test control. Normally, the component of a block level environment make a combined decision of when it would be appropriate to test and to end the test. This can be a mixture of active stimulus decisions and passive observation, such as waiting for an ongoing transaction to end. The usual mechanism for controlling test follow is called objection. Basically, any component can object to the test ending until it sees fit. However, when the passive block level components are used in the top level component, it may no longer be appropriate for the monitor on internal interface to object to test completion. For example, we must be able to tolerate termination of test during the partial transaction on any one of many internal or even external interfaces. Likewise, direct memory access to DMA transfer need not necessarily complete if the top-level scenario does not require this. This is another case where the passive component, like a monitor or scoreboard, needs to be aware of the passive or active or passive flag in order to behave appropriately. Do not control end of test from the component in passive mode. I. Stimulus reuse. When on block level verification component reuse in effective mode as part of the stimulus hierarchy in top level environment, additional care is required with the sequence API. Top level stimulus is typically more constrained than the equivalent stimulus at the block level, and normally the stimulus is encapsulated inside a higher level protocol of running in parallel with the multiple verification component to create interesting scenarios. It is not appropriate to put too many constraints into sequence item. For example, distribution constraint, since the user will typically not generating items directly, but rather most of the user constraints used reside in the sequences, and the sequence item should only contain the legality constraint. Put user constraint in sequences, not sequence items. Likewise, the sequence API should not be at too low at a level for the top level scenarios generator, that is, with all sequence item fields exposed as control nodes. But rather powerful high-level functional sequences should be provided, as well as more generic low-level sequences. It's unlikely that the block-level suppliers that predict all use cases in top-level environment, but they can provide a comprehensive sequence library that supports the full functionality of the verification component protocol. If the verification component has more than one active agent, then the user component supplier should encapsulate all sequences into a single sequence library registered with the highest level virtual sequencer in the verification component environment. Provide a comprehensive sequence library that encapsulates low-level and high-level functionality. Chapter 7. Problems of Scale. The sheer scale of the integrating many block-level components into a single top-level environment introduces additional demands on block-level suppliers related to build, encapsulation, configuration, namespace isolation, and interface operation that may not be at all apparent when working in a block-level only domain. Consider these and for the potential headaches involved with the badly encapsulated block-level reuse as shown in Figure 4. Unencapsulated reuse. Typically, the top-level verification environment is already complex with many external interfaces and internal paths all operating in parallel, and of course the full scope of DUT behavior needs to be catered for, including models, analog blocks, clock domains, and power islands in order to support the top-level team in validating the verification requirements. Necessary for tape-out, and block-level suppliers have a duty to make things as easy as integrated and reused as possible. A. Environment encapsulation. Typically, it is the entire cluster of the component from the verification environment that is required for reuse, excluding the full top-level list, but it is not appropriate to expect the top-level configuration and connect the various low-level verification component into appropriate topology, but rather this must be provided by a block-level environment encapsulation itself. The chances are that this encapsulation is already done to some degree in block level environment, but the real question is if it can be used as is without having to copy additional coding into the top level environment. For example, if the block level environment topology is put together in a base test component, then it is by definition not reusable since tests are not ported to the top level. Likewise, if the uppermost environment in block level does not consider active or passive settings and the environment needs additional work before it can be reused. The best solution here is to encapsulate all components and settings into a single environment component and use it in both block level base test and the top level environment. Encapsulate all sub-components in a single reusable environment. B. Configuration encapsulation. It is assumed that the most block level verification environment make use of multiple interface and module verification components, each of which must be configured to match the requirement of the block. It's not appropriate to pass the responsibility for configuring all these sub-components up to top level. Let the block level, the environment should configure the all lower the level things that invariant for block in this project settings and encapsulation. A few block flexible configuration settings remain into an object made visible to top level. Hence, the top level environment only has to care about one configuration object for each complete block level environment, and the configuration object only provides a relevant field that can be changed in the environment. Encapsulate configuration object correctly and manage content. C. Interface encapsulation. Normally, each agent in the verification component with an environment has its own dedicated interface constructor handling a single functional group of signals. With several verification components grouped together in the environment, we end up with several individual interfaces to instantiate, connect, and associate with virtual interfaces inside the class world. This is not usually a problem until we consider the scale of the top-level environment encompassing many passive block level components. Under the constant circumstance, it's not appropriate to present the top-level integrator with a set of the fragmented signal interfaces or signal maps for E. In order to reuse a single block environment, and specifically, there is a real danger of missing a vital connection, making incorrect connections, or failing to associate it with the virtual interface references appropriately. This risk is compounded because the reused block level environment is connecting to the internal signals in the DUT using white box proving and not external ports. So we need to communicate more precisely exactly what needs to be connected for the block level environment to continue to operate the best way and the best way to do this is through encapsulation. The block level suppliers should provide a single hierarchy interface which instantiates the required lower level interfaces. This interface encapsulation enables more effective white box probing of the embedded block and the DUT. Since the only HDL path to the embedded block is required and the top-level integrator only has one virtual interface assignment to make. Combine multiple signal interfaces into a hierarchical interface. D. SVA encapsulation. Functional protocol checks are often implemented using SVA and therefore they cannot be located in the system variable classes for the verification component to which they are belonging. These assertions should therefore be located inside the corresponding signals interface construct for the verification component so that they are automatically included when the interface instantiates the test bench module. There is no need to independently bind a collection of block level assertions that belong to the verification component to the internal signals in the DLT, since the content connectivity is required for the interface signal collection anyway. Design assertions that are not embedded in RTL will have to be handled separately, so this can also be achieved by encapsulation inside an interface construct. So encapsulate has to be protocol checks inside the interface. E. Namespace collision. Importing multiple packages into the same scope can cause namespace collisions if the artifacts in each package are not correctly named. This is not just restricted to global constructs like a macro definition, but also class and constant and type definition with each package, including enumeration literals. The increased scale of the top level is much more likely to uncover namespace collision than individual block level environments, since many packages are imported into the same scope. In general, things like constant definition and class names do not suffer from defect here, but the smaller items get overlooked. For instance, it's not appropriate to have a bus with macro definition, since the top level there is many buses which with different words. Likewise, it's attempting to the short course names for the enumeration iterators inside an enumerate type definition, for example, idle. But when multiple packages are imported into the same scope using the wildcard operator asterisk, any enumeration literals with the same name collide even though the enumerate type name itself may be unique. The recommended approach is to prefix or name them in items visible in the package scope, for example, class, constant, macro, and types, but not macro numbers, with a unique string derived from the verification component name. Avoid namespace collision by using unique prefixes to the package scope. F. Benefit of the encapsulation. Following the guideline for correct encapsulation and naming of the block verification component, and environment results in much easier and less error-prone integration into top-level test bench. The resulting environment is more modular and easier to maintain as well. So, Figure 5 illustrated improved encapsulation compared with the shown previous in Figure 4. Figure 5 encapsulated reuse. The Section 8. Chapter 8 Additional consent. Not all vertically used consents are directly related to the change of role associated with the block level verification environment being reused in the top level hierarchy, although that is the focus for this paper. This section outlines some additional consents that need to be taken into account in many projects and is included in order to give the reader a more comprehensive view of the overall problem space. Unfortunately, a detailed analysis of each of these topics is outside the scope of this paper. The formal verification. Formal verification is normally applied at top block level due to tool limitation and the need to be contain the scope of the mathematical proofs. Vertical use of the formal verification artifact is a how not only desirable but also a requirement in order to ensure correct integration and dynamic operation of the associated block. In particular, it is essential to validate that the assumptions used in the formal analysis hold true in the top-level environment by using the assume statement as the assertions in the system-level environment. The functional properties may, in general, also be reused in the top-level environment to validate the correct dynamic behavior of the block and provide confidence on the accuracy and completeness of the formal analysis. Validate assume statements from the formal verification. The B. Power-aware simulation. Most block-level verification components do not execute power-aware simulation, yet this might well be the critical verification requirement for the top-level environment. Specifically, both signal-based transactors, for example, drivers and monitors in the verification components and associated with the SVA checks may not behave correctly or recover in an appropriate manner. If the signals include the clock and reset, transition to undefined values in the top-level simulation due to the power domain manipulation, or verification component and application where power-aware simulations will require need to take power intent attribute into account. As minimum, the driver, monitors, and SVA checks need additional power state indicators which can be used to prevent false failures and ensure correct recovery from the power of state and of course validate the actual power state sequencing. If the block level verification requirement including power intent simulation, then the corresponding metadata must be correctly encapsulated for reuse in a higher level environment. Verification component must be power aware for lower power applications. C. Assertion-based verification. Many RTL blocks are implemented with embedded or separately bound assertions intended to validate important design requirements. These assertions can be invaluable in detecting and isolating functional failures and abuse of the RTL block in the top-level system. However, the caution is required. The typical RTL assertions are focused at a very low level and could therefore quite significantly affect the performance of the top-level verification environment if all the assertions for all blocks are active and evaluating more property on every clock cycle. Having many thousands of the relatively uninteresting design assertions can also contribute to the also sense of the security. These assertions are only valid if they really protect the block the misuse or they contribute directly to the top-level verification environment requirements. For some reason, the quality of the design assertions varies significantly, perhaps due to the different mindsets of the originators. While this situation might be tolerable at the block level, it can be a killer in the top-level simulation. Block-level RTL assertions should be well documented and encapsulated such that individual checks can be selectively enabled so it disables the top-level environment. This can be achieved using leveled by assert statement in SV or by providing control nodes continuous assertion embedded in supplementary checker code. Enables only appropriate RTL assertions for top level. So D top level and D clock domain checking crossing CDC clock domain check crossing. Verification of the CDC clock domain check crossing signals is almost always part of the requirement for modern top-level environment. Even if the CDC behavior is partially visible at the block level, this might not be enough to validate the interaction of all clock domains at the top level. This is especially true when the lower power features like dynamic voltage and frequency scaling DVFS are controlled by the application-specific software. For example, if the CDC assertions are available for the block-level environment, then these should be reused at the top level as discussed in the previous section. The reuse CDC assertions in the top level. For the bottom-up, the CDC flow, it is also possible to attach the waiver the block level artifact in the important this the top level analysis in order to minimize the information overload often associated with the full chip CDC analysis. Note the power, however, that the extreme caution is required here since the clock relationship and the operational both may not be fully understood at the block level and can change for new derivatives using the same legacy block. Exercise caution in the bottom of CDC waiver reuse. E. Transaction level operation. An additional application of vertically use constant targeting verification component to operate with the different abstraction level for the DUT, for example RTL, and transaction level system C models. Typically, the same environment could be used to validate the cycle accurate system C models and the RTL implementation. In fact, the system C model does not normally have to be cycle accurate, but does require a signal interface for this to work. However, if the verification requirements needs to be support transaction level modeling without a signal interface, including stimulus and monitoring, then the driver's monitors need to be designed with that in mind. So this would typically involve separating protocol layers from the physical signals interface layer in the agent architecture. When done correctly, most of the remaining architecture is unchanged and reusable between the two abstraction levels, including sequence libraries. The checker operation, especially scoreboards and functional coverage. Supporting multiple abstraction levels requires architecture for partitioning. F. Analog mixed signals. Analog mixed signals AMS simulation is used to validate correct interoperation of the analog and digital subcomponents. These simulations are usually done at the block level due to the tool performance issues involved with evaluating continuous analog behavior as opposed to the discrete event-based digital simulation. The AMS simulation environment is also used to validate the behavior models of the analog blocks, which are then used in the higher level digital simulations. Typically, the behavior models would be instrumented with a comprehensive set of assertions, either actual or analog SVA or the ad hoc continuous assertions. Often, these assertion style checks are extremely inefficient and can severely affect the performance in the top level environment if the DUT has significant analog contents. For that reason, the analog assertions also need to be well documented in the individual controllable in order to get the most effective usage checks and support the top level verification requirement without compromising overall top level regulation effectiveness. Enable only appropriate AMS assertions for top level. G. Emulation and acceleration. Many top-level verification strategies make use of the hardware-assisted emulation or acceleration to enable much faster simulation of scenarios closer to a real application speed. This environment is synthesized DUT and part of the test bench. Typically, they use both functional signal interfaces as well as both RTL and test bench assertions into actual hardware efficient in the emulator system. The remainder of the test bench runs in simulator, which communicate with the emulator box interactively during test execution. Architecture guidelines for vertical use in the emulation systems are outside the scope of this paper, but some limited information is available in 6. The H. Multi-language operation. Another aspect of the verification reuse that should be mentioned for completeness is that the multiple language interoperation. Most simulators support the ability to operate with different functional languages such as E, System Verilab, and System C. However, the actual verification component from each language do not communicate in a standard manner, and the current situation is far from the desired plug-and-play scenario. Relevant topics include coordinating of the phases, scheduling and configuration stimulus generation, constant serving and data communication, message maintenance, and the functional coverage unification. The full analysis of this topic is also outside the scope of this paper, but more information is available in 7. 9. Tuning reuse. Taking into the account the change of the role associated with the vertical reuse and the different focus for the higher level verification and requirements, many block level components need to have the behavior modified in order to add the value in the top level environment. A. Tuning coverage. Since the top level environment has different verification requirements, it's unlikely that the block level functional coverage groups can be reused effectively without modification. The top level environment makes use of the block level decoding capability and coverage collection mechanisms, but may require to modify the actual coverage groups and beans for each cover point. In addition, top-level environment needs to create additional coverage to measure the relationships between the different blocks and subsystems, which can be layers on top of existing block-level mechanism. Verification environment using E-language can tune coverage directly using the aspect-oriented programming AOP mechanism to refine the original classes as a system value component environment needs to be overloaded the coverage group definitions, typically by using a factory patterns to do class substitution for regions as provided by UVM. In either case, the functional coverage code is quite different to normal functional code in the corresponding monitor component and benefit from the correct encapsulation in a separate coverage-only class definition. For system value, it's essential that it's only the coverages associated with this in this class enable safer factory class substitution without affecting normal monitor behavior and minimizing the maintenance problems when the bugs are fixed in the monitor functional code, whereas this just represents good coding practice. Encapsulate the functional coverage construct in dedicated class. There are several models in the doing coverage encapsulation. The most appropriate for a particular application depends on the coverage requirement. Valid options include instantiated a coverage class in the monitor, extend the monitor to add only coverage code, so to provide a subscribe class coverage component. Instantiating coverage class inside the monitor is the most flexible solution and can provide transition coverage as well as cross coverage of the other monitor utility field. Subscriber coverage is limited transition content since it relies on the transition being published to trigger the coverage collection. Extending the monitor to add coverage can lead to a complication if the factory is used to replace the original monitor with a modified class. B. Filtering messages. It is absolutely essential that the used block level environment do not upload the top level log files with excessive information about block behavior except when the required configure to do so by the controlling environment. This is also somehow related to scale. At the block level, where we probably do not care if we have too much information about this particular block. Since that is the focus for the test, and as a result, inappropriate messages with incorrect verbosity settings may be present in the final environment. Examples of such defects include printing messages without a verbosity control, for example using system value display function, or unguarded item print, or printing too much information at too low a verbosity settings. For example, printing a complete transaction at low verbosity. Typically, the top level will disable all messages from the block level component during regression runs and only selectively enable messages generation for the block level environment in order to debug errors. Errors and warnings are not affected by verbosity levels and are always printed. The block level should stick to a simple verbosity scheme, such as that shown below. The supplier should check this as part of the release procedure by actually running the block level regulations under different verbosity settings. Low message that happens once per run or reset. Medium, single line summary of each transaction. High, print each transaction or sequence once. Full, anything including method parameter settings. Ensure messages purpose is appropriate and controllable. See controlling checks. In general, we expect to reuse all available checks from the block level environment in order to validate continue to correct operation of the block embedded in the top level duty. However, there are some checks that might cause problems due to the different use case. One good example of this is an end of test checks for a scoreboard, which generate a failure if the scoreboard is not empty. At block level, this is appropriate behavior since the environment is in control of when the test ends. However, at top level, different criteria apply for the managing end of the test conditions as previously discussed. In this case, the user should provide a separate the controlling the flag for the test scoreboard check so that the user can disable this check if required. Typically, disabled checks should be generated warning instead of an error under these circumstances. Allow checks to be disabled where appropriate. X. Retrofitting the reuse. It is not appropriate necessarily to validate internal top-level verification required by applying the reuse strategy, since we could choose to develop the additional that monitors coverage and checks independent of the block level components. Reuse does not come to free, but the implementation effort is not huge and generally much less than the cost of reinventing the code, especially in terms of the engineering time. In reality, the trade-off is generally not a choice between opting to reuse or reinvent, but rather than whether or not to validate some of the internal top-level verification requirements at all, which carries an extremely high price tag in terms of quality and risk. It would not be far off the mark to assume that its verification component has not yet been reused in a different context and is not reusable. This good news is that retrofitting the reuse to an existing environment is a feasible proposition and effort can be justified by consumers' project as a cost comparison between the modifying the code for reuse or reinventing from scratch. It is very unlikely that the cost of fixing the even seriously broken block level environment will be more than coding a passive equivalent from the scratch. In addition, the changes to support vertical reuse are generally related to the encapsulation and composition, and therefore they are relatively low risk in terms of introducing bugs, but just to show up as a compiler and elaboration types of error. The following flow can be used. Determine the scope of the effort, review against the reuse guideline, and implement all pairs in the supplier's codebase. Validate changes using block level regression. Experience suggested that determining the scope of the effort is usually hampered by out-of-date and inaccurate documentation for verification environment, or indeed no documentation at all. However, using the factory.print mechanism from the OVM and UVM or the eDocs facility from Spamman is usually a good place to start to explore the actual topology of a supply the verification environment. It is absolutely essential to have a working block level regulation to facilitate code improvement and preventing the accidental damage. Once the reuse enhancement have been retrofitted to the block level environment, it's time to test it out. Instantiating an extra instance of the block level environment in the block level base test and configuring it as passive operation as shown in the figure 6 is a great way for a supplier for integrating to weed out most of the reuse defects described in this paper. This extra passive environment shadow the normal active testbench behavior Its only purpose is to validate the passive operation of full block level environment. Instantiating a shadow instance of the environment in block level based test. Configure the shadow instance to passive mode, learn block level regression. Figure 6 is the shadow passive environment. To validate passive operation in block level environment. Once passive mode has been validated in the block level environment, an instance of a passive environment can then be integrated into the top level environment and attempting to tune the coverage, control the messages, and validate if any checks need the additional control flags to be disabled them. Instantiate the passive instance in the top level environment, validate the coverage tuning, and check control and the message verbosity. Any defect or improvement should be fed back to the supplier's code base, which will ensure much more effectively use for other consumers at a later date and effectively improve the quality of the block level verification environment. 9. Conclusion. Many of the guidelines presented in this paper are standard engineering practice and are repeated here for completeness, together with additional guidelines based on real-life experiences. The techniques discussed in this paper have been successfully used and adapted at a number of different verification groups and various clients, and it is hoped that combining programmatic observation with comprehensively used guidelines and practical suggestions for the retrofitting the reuse into real-world project will empower the reader to achieve the improved vertical reuse in their own project scenarios. Okay, this was quite a long paper or the guideline. The title is Pragmatic Verification Reuse in a Vertical World from DVCON 2013. Thank you for your time. See you next time.